All right, we got a few more 2D kinematics examples, primarily of the launch variety. That's most of what we look at, but we're going to do them. So this first one is primarily distinct from other problems because it uses angles more than it uses time. So let's go ahead and look at it. First thing I want you to note here, right, is we got two triangles, right? We've got this 20 per second, 30 degrees above the horizontal. So we got V, if we want to draw a V initial triangle, we can. We've got 20, initials 20. We've got 30 degrees, right? And on the two sides of that triangle are V initial X and V initial Y. And then we've got this hits the ground at a speed of 30 meters per second. Okay, so we don't know exactly what that is, but we know that it's down and sort of to the right, right? So we've got, if we were to draw a V final triangle, it would be V final is 30, and V final X, and V final Y, right? So we can do this here. So we're going to split this again into X and Y components. So we have delta X, V initial X, V final X, AX time, and delta Y, V initial Y, V final Y, AY. And we know for a bunch of these are like AX is 0, AY is negative 9.8. We also have V initial X and Y we can find using trig. So V initial Y is 20 sine 30, which is easy, that's 10. And V initial X is, you gotta do the cosine thing, right? It's gonna be 20 cosine 30, and that's just like not as easy to like do in your head, but I did it ahead of time, and it's about 17.3. Okay. Now, looking at this, we don't have anywhere near enough information to solve for any, like, you know, to do kinematics in either of these directions. But we do have one thing. If acceleration x is 0, this just means this is 17.3. Still don't have, I still can't find time, right? And by the way, I guess we should say I'm trying to find change in y. I still can't find time because it's this combination of three variables doesn't let you solve for anything else. So I can't find time. But what I can do is I can go to this triangle. If I know this is 17.3, I can find v final y, because v final squared was v final x squared right, plus v final y squared. And that allows me to find v final y to be negative 24.5. And notice it's negative, right? Because I know it's going down. We take the square root of that. It doesn't really matter in this. Actually, well, depends on how you're solving this problem. It may or may not matter. But I do know that it's going down in the y direction. So it's got to be negative 24.5 in the y direction. That leaves me with, now, three variables in the y direction, which means I can solve for the fourth. So if I can do it with, let's not do that equation. That would be silly. V final y squared equals v initial y squared plus 2a delta y, 2ay delta y. So negative 24.5 quantity squared. So again, if you do it this way, you actually don't, it doesn't matter, that's negative, but it should be negative. Equals 10 squared plus, which that should really be minus at this point, right? Because we have acceleration is negative. So minus 19.6, right, times change in y. This is a pretty straightforward problem. We can solve for change in y is equal to negative 25.5 meters. Alright, so to go back to the whole purpose of this example problem, is in a previous problem we looked at time. We looked at time as a way of connecting our results from, connecting our variables, from x to y. But in this case, we didn't have that. We couldn't use that time variable, but instead we had this additional information And we were able to use triangles to connect x and y. So we got this x value. Couldn't use it to get time, but we could use it to get this y value. So just be aware of the ability to use triangles, especially initial velocity and final velocity triangles, to go from x and y just as much as you can time. All right. What angle maximizes horizontal displacement for an object launched from ground height? So you hopefully already know this because of that diagram I drew or we had in class. But let's actually do the math here. So we make an assumption, right, that as we split in x and y, well, let's actually draw it. Let's start with drawing here. Right, I've got flat ground. I've got an object. Up, and it lands here. And what I want to know is what is the angle here that makes change in x the biggest it can be. Okay. So first off, we're going to assume that the initial velocity doesn't change. Otherwise, obviously, you throw it harder, it goes farther. We're going to say, okay, initial velocity is constant no matter what angle. Hopefully that makes sense. So we've got some angle theta, where we have v initial x, and v initial y. Okay, so let's roll through what else we know. So change in x equals 0. Change in y, change in x doesn't equal 0. Change in y equals 0. Not bad. Right, the height doesn't change, it's on level ground. V initial x, we can just say is v initial cosine theta. V initial y, let's say is v initial sine theta. V final x, v final y. Ax equals 0. Ay equals negative 9.8. And we have time. So I want to figure out I sort of want to solve for displacement x and then figure out what makes that bigger and what makes that smaller. So I need to get a time here. Now there's two sort of ways to do that. There's an easy way and a hard way. Okay, we're going to do the easy way here because I'm lazy. When we talked about this level height thing, what we know is that as long as, like we know from 1D kinematics, that as long as the x, as long as we end up at the same height we started at, there's symmetry in the y values. So v final y should equal negative v initial y. So this is negative v initial sine theta. Okay. All right. With that, I can then do v final y equals v initial y plus at. It gives me negative v initial sine theta equals v initial sine theta minus 9.8 times t. Do this, t should come out that 2 v initial sine theta over 9.8 is the time. And then plug that into displacement one, or the x variables. So I can get change in x equals v initial x times time. V initial cosine theta times 2 v initial sine it's a little bit v initial sine theta all over 9.8. Now this is kind of a gross thing, but there's actually a trig identity here. If you don't remember this, that sine of 2 theta is equal to 2 sine theta cosine theta. And I have this 2 sine theta cosine theta. So this becomes v initial squared sine of 2 theta over 9.8. Now, obviously, right, as you make v initial bigger, displacement gets bigger. No shock there. But the other thing you notice is that angle does matter. Angle does affect it, which we could have guessed, but it's interesting to see how it does it exactly. We know how to find the maximum. Sine of 2 theta is max at theta equals 45. right? Because sine of theta is maximum at 90, so if I make 2 theta 90, it maximizes it. So max theta is 45. Or the maximum distance occurs when theta is 45. Okay? There's a second part of this that's interesting. What it means is what sine of 120 is equal to sine of 60, for example. That means that the angle, if theta is equal to 60 or 30, it should go the same distance. And in fact, we get this sort of symmetry around 45 degrees. The distance it goes should be symmetric around 45 degrees. 40 and 50, same distance. 35 and 55, same distance. That sort of thing. Okay? All right. Last problem here. All right, I just had to edit that because I made some mistakes, but here we go. So we're shooting at a falling target. Okay. What that means is that we've got this projectile. We're going to launch at a target that's currently stationary, so v initial equals 0 here. We're going to launch right at it. And just to give us some numbers, this is 20 meters, and this is a 30-degree angle. Okay, so 30 degrees, 20 meters. That means this is 40 meters, which means, and this is 40 cosine 30. It also means that our initial velocity, right? And I'm going to give you our initial velocity. Initial velocity of the projectile is going to be 30, and that means that v initial y is 15, and v initial x is, this is changing x, is 30 cosine of 30. Okay, now here's an interesting problem with this, right? So we launched this object pointed directly at it, but actually it starts to arc. It hits here. Meanwhile, the object is falling. And the question I want to know is, does your projectile is high or low as it falls? Okay. So first thing we can do here is I want to look at what height the projectile is when it crosses this distance. So whatever this distance is, I want to figure out how high it is. Okay, so we have the initial x is 40 or 30 cosine 30, and there's a reason I'm not simplifying that. Change in x is 40 cosine 30, and acceleration of x is 0, which means I can find time from this. So change in x equals v initial x times time plus, well, this is all going to be 1/2 times at squared, axt squared. That's all 0. So if I actually do this, I get 40 cosine 30 equals 30 cosine 30 times time. And the cosine 30s cancel out, which is why I didn't bother to solve them out there. Okay, so then I get that time is equal to 4/3. I then I can go to the y component of this. Again, this is of the shot. So v initial y is 15. AY is negative 9.8, and I just found that time was 4/3. So if I put that in to the change in y equals v initial times time, y times time, plus 1/2 AY times time squared, right? I should get that change in y is equal to 15 times 4/3 minus 4.9 times 4/3 squared. And between those two things, I get a displacement of 11.29 meters. So it doesn't hit 20 meters, it hits like a little over halfway up there. Okay, when it gets through here, this height is 11.29. But what about the target? Where is it? So for the target, again, we also want to consider the time. The v initial is 0, the AY is still negative 9.8, and the time is still 4/3. Because again, we want to consider where the target is and where the projectile are at the same time, at the same moment. And we can solve that again with the same equation. Change in y equals v initial y times time plus 1/2 ay t squared. T into t there, t squared. When we simplify that, we get change in y equals negative 8.71. Okay. Now what does this mean? It means that it fell 8.71. And in fact, those two things together add up to 20, which means that the projectile will hit exactly on the target in this case. And that actually should make sense, because what we actually want is we want change in y projectile minus change in y target to equal 20. Okay, and if we actually solve these two together, we get 15 times 4/3 minus 4.9 times 4/3 t squared plus 4.9 times 4/3 squared. And so these two parts cancel out, leaving just this, which is of course 20. Okay, these two parts should cancel out always, the acceleration times the time squared. It works out. All right, that's it.